Uh, Good morning, everyone. Welcome to the first session of the second day of the COS meeting. I'm Jubi Son from SNU. I'm the chair of this session. It is my great pleasure to introduce our speaker today, Professor Satoshi Miyazaki from NAOJ. Professor Miyazaki went to University of Tokyo, the physics department for his undergrad and the graduate program. So he earned a PhD, and then he did a postdoc for a year at NAOJ, and then he did a postdoc for 2 years at the University of Hawaii. And since 1996, he became a faculty member at the NAOJ. He's world-renowned camera builder, so he participated in the Prime Cam development, and he was the PI of the Hyper Prime Cam, which is a flagship instrument on Subaru. And most importantly, he's the director of Subaru right now. So he came to visit us to talk about the possible collaborations, future collaborations between Subaru and the Korean Astronomical Society. So please take the floor.
Thank you. Thank you, Jubi. Good morning, everybody. I'm Satoshi Miyazaki from Subaru Telescope. The reason why I'm here is introduced by Jubi briefly, but almost at the end of the talk, I will talk a little bit more why I'm here. But today, I'm going to introduce you about Subaru Telescope in general. This is how the primary mirror looks like, so over the ground-based telescopes all over the places. And as you can see, the GNP and the TMT is being, built. And under such an occasion, 8-meter class telescope is no longer unique, but ubiquitous. I think it's more than nearly 14 8 to 10-meter class telescopes all over the world, and the Subaru is just one of them. So, but we have some very unique feature, which is the prime focus for the 8-meter class telescope. Because the prime focus has the shortest focal length compared with other 4C like Nasmyth and Cassegrain, that gives us a wide field. So we attach the telescope the camera on top of the telescope right here. And Subaru uniquely realized 1.5 degree field of view on 8-meter class telescope. So this means that, we are very good at the surveying faint objects because the primary mirror is large and over the wide field area of the sky. And also another feature is, of course, amount of care, which provide us a very superb image quality, like a 0.65 arcsecond thing. So on top of it, we put this type of gigantic camera, which we named the Hyper Prime Cam. And because it's camera, they have a standard equipment like lens, filter, shutter, CCD like this. So it's basically nearly the 1 gigapixel digital camera, but the size is big, like 3 meter high, and the total weight of this camera is nearly 3 tons. This is a graphical view, but in the real life, the camera looks like this. This is myself, 180 centimeter tall, and the camera is 3 meter tall, like this. And the lens is the first lens of this camera is 85 centimeter in diameter, and that is fabricated by Canon. That is Japanese optics firms. Okay, and the CCD is also built by Japanese semiconductor vendor, Hamamatsu Photonics. This CCD is jointly developed by NAOJ and Hamamatsu. It's the size is 6 centimeter times 6 centimeter on the longer edge and 3 centimeter in the shorter edge, and 2K, 4K pixels. 15 micron square pixels. And the feature of this CCD is its thickness. Usually the thickness of the CCD for the commercially used CCD or CMOS is like a few micron, only few micron. However, this CCD has a 200 micron thickness. The advantage of this thickness is that giving you the very high QE in red. This is the QE diagram. Horizontal axis shows the wavelengths from 4,000 through the 1 micron. And the quantum efficiency is vertical. And so this is a sort of typical CCD curves, but what we have developed is maybe, almost 4 times higher QE in the 9,000 angstroms. No, yeah, 900 nanometer. And this blue curves is a QE curve of the CFHD megacam. So it's a, advantage is very clear because the QE, 4 times higher QE means that already, the diameter of the telescopes is equivalent with the diameter of the telescope. It's twice as large as. So developing this type of, high QE CCD and detector is very, very important in parallel with the the effort to build a large telescope itself. So because this CCD is only like 3 centimeters times 6 centimeter, but our focal plane is like this big, 50 centimeter. 50 centimeter physically, 1.5 degrees. So one CCD is not enough. So we mosaic them. 116 CCDs were mosaicked like this. So CCD installation was made a long time ago at the NAOJ headquarters clean room. And this is myself. And I, unbox the CCD from the package and do some electrical testing and hand it to the other person, which detached the protector. And she handed to the third person who is not on this picture, but he installed. So 3 of us keeps doing this type of sensitive job over the week. And eventually the whole focal plane were assembled. That has 116 CCDs in total. It's, well, I can skip it here. And the CCD electronics is also inside the cryostat, like this, and all the messy cables inside, and we have to deal with those type of many channels of this signals, and eventually it looks like this: the focal plane and cold plates on it, and the electronics assemblies are located behind the focal plane. Right. So this is the final assembly phase of the camera. The dual window whose size is, the thickness is 37 millimeter. So nearly 20 kilograms windows are being installed at this moment. And then, this is the final appearance. Yeah, the filter is also large, like 60 centimeter in diameter. Shutter is also customly designed and made and assembled at the observatory. So this shutter has 2 screens, and this, you can run this 2 shutters simultaneously, and we can adjust the width of the aperture, the slit, to control the exposure time in the shorter domain. But anyway, this is all designed and built by us because nobody sells this type of things. There is no commercial available equipment. So it's kind of fun to build something really new like this. Okay, so assembled together, and when we attach the telescope, the observing obtained image is something like this. And this camera covers most of the bright part of the Andromeda galaxies, like this. And so usually we use this camera for the surveying, and we did 6 years surveys, and it was ended 2 years ago, and 1,000 square degrees were covered, mostly along the equators. We set our observing fields, and some fields are set at the northern field because we are collaborating with Margaret Guerra. And she has a whole bunch of spectroscopic data up there. So we did cover that. And let me show you how the image looks like. Let me move into some part of the sky, which we call the cosmos field. So this is all galaxies mostly, 90% or more than 90% of galaxies. And faint galaxies like 26, 27 magnitudes are easily visible. And this is a part of the class of galaxy in the cosmos field. I think also I will give you, oh, sorry, still going on. Maybe we are moving to the constellation Virgo, and somewhere in the middle of the Virgo, we can see this type of very gorgeous class of galaxies. That's Abell 1689, the redshift of 0.18. So this is a very famous class of galaxies. So this is also taken by Hubble. So you can compare the Hypers prime cam image and Hubble. And Hubble image is, of course, sharper like this. But when you really care about the galaxy itself, whose intrinsic shape is extended a little bit, like 1 second or 2 arc-second, if the target were such galaxies, I think that the total depth limiting the magnitude is almost similar with Hubble's. And we can do many things using this very wide field data sets. Okay, because we have a whole bunch of galaxies, we can do many things. But one of my favorite is doing some recleansing business using the faint galaxy to probe the dark matter distribution like this. And of course, we do some 3D lensing analysis, which is published a few years ago. And I think this is the widest dark matter 3D map. And of course, James G is also this instrument very well. And actually, he published a very nice paper very recently on Nature Astronomy based on our public data sets. And he's a very clever guy and did a very nice job. And we are very happy to know that because our data set is quite useful. So anyway. Okay, but anyway, you please visit the website HSC Map, where you can take a look at such images on the web. I mean, that I can show you through the movie. So this is a comparison between other project. Ours is right in the middle, HSC, and we listed up the A omega, which is a metric of the survey speed, basically the mirror area times omega, I mean the field of view in square degrees. So compare with the DES, the DE-CAM, which almost started the operation quite similarly, like 2012. So we were a rival together, but our A omega was 3 times higher. But of course, US is doing another project, which was called LSSD, now Rubin. Rubin is more powerful than us, like 3 times or more. And they are coming to the in a year or so, or a little bit longer. But so when LSSD comes online, HSC is become a sort of obsolete. Of course, it's the most powerful camera on the northern hemisphere, but still, when you look at around the world, LSSD will dominate, and they can do the very first survey very rapidly, which will be, I think, their service speed is, in reality, service speed can be 20 times faster than us, because they can use the whole night for the observing, the imaging. They don't have any other instruments, so they don't have to swap the instruments, then they can keep going. So their service speed it can be 20 times faster. So our strategy is that something really unique. So HSC is no longer unique when LSSC comes. Our new instrument is going to be PFS, the prime focus spectrograph. The prime focus spectrograph, so instead of the imager, we're going to put the fiber positioners at the prime focus, and that the light will be fed through the fibers and comes to the spectrograph unit located somewhere around here. And this is being prepared for more than 10 years. But now, well, I can say that it will come. And let me show you the latest status of the PFS as of March 2024. This is a result from the last commissioning run. So where you can see this, so the horizontal axis is wavelengths from 400 through the 1.2 micron or beyond, and vertical axis is the object ID. So the multiplicities of the spectrograph is at 2400. So that is biggest among the 8mm class telescope. And also that covers near infrared. US DAISY project doesn't have any near infrared range. So that's very useful for the many other projects like a galaxy evolution. So I think this is very unique and powerful instrument. But you can see some blank area. Two IR camera at this moment that had some maintenance during the work. The commissioning, and the one blue camera also had some maintenance during that time. So, but they're all almost fixing, and all those gaps will be filled by the end of this year, clearly. So this is the prospects. After a few more commissioning runs scheduled in 2024 this year, and we really expect that it will be fully operational from February 2025. And about half of the PFS time will be used by Subaru strategic program, whose call for proposal will be out soon. And I think the builder is definitely the builder of the PFS, and the team will submit it. But in principle, anybody can submit a proposal for this big chunk of the time slot. And another half will be open for public, Japanese public, but also include the University of Hawaii time and time for Keck and Gemini exchange framework. So the Korean people have access to Gemini. So perhaps in principle, you can apply for the time through Gemini for this PFS. And also we have other instruments in addition to the HSC PFS, which is one example is extreme AO at the NASMIS foresight focus, and in combination with infrared imager, they do exoplanet direct imaging shown like this. So this is a snapshot of every few months, and you can clearly see the movement of the exoplanet around the main star. And this was published last year on Science magazine. And this clearly demonstrated the stability of the Subaru telescope. So this is another nice feature of Subaru mechanical stability and very good instrument suite. Another thing is the ground layer adaptive optics project, and that will be explained in more detail by Koyama-san following my session. I think the room is different. That what I was told, but so if you're interested in this opportunity, so they're trying to realize basically the 0.2 arc-second infrared imaging over the 15 arc-minute field of view, 15 arc-minute and 15 arc-minute. So I think the 20 arc-minute across. And compare with similar instrument realized on the VLT, then we have a 7 arc-minute field of view. So I think they try to make this field 4 times larger than VLT. So I think this is very ambitious and it's going to be very interesting. Okay. Some of the instrumentation, which is not perfectly unofficial. This is my hobby project for the new instrumentation after HSC. And I'm still working with Hamamatsu Photonics to do some new things, which is basically the high-speed CMOS camera. The director of Subaru is not easy. It's super different from astronomy or astronomy instrumentation works. I need this time for hobby. And I keep this sort of small experimental set up at my director's office. And everybody laughed at that, but I really need this type of things to keep me up and running. And so I think if you are X-ray astronomers, you can understand the meaning of this view graph, but yeah, they give us a very nice high resolution in the X-ray, and the readout is quite raw, like 2.5 electrons. And compared with CCDs, it's not so different. There's some escape, but it's almost okay for the visible astronomy. So we are building this small camera to test this new CCD. It's already back illuminated, and this size, the size of the sensor is similar to what we adapted for HSC, and this is how it looks like and assembled together. So we did some testing at 1.5 millimeter telescope at Hiroshima University back in the day, just before COVID, and compare with other program. I think Subaru CMOS. We will start from the small camera, which was whose prime focus unit was used for the original prime cam, and the original prime has been already retired after the installation of HSC. So we recycled it and the original prime cam system, and then replace the CCD with the CCDs and cover the same similar field and 0.25 square degrees and do some really new things. And so I believe this is another uniqueness, but of course this is just my hobby project, so I cannot use my Subaru staff member to do this. I just work with students and postdoc which I hire. So, but anyway, so I think okay, I only have 10 minutes to go. Right. So from here, I will introduce you something different, which is the Subaru international collaborations so far, established so far. So, so we have a very unique ground-based telescope that is a Subaru that I just introduced you. That is a wide field imaging camera. It is being already up and running for 10 years, nearly 10 years, and multiple object spectrograph. Oh, sorry, this was wrong. 2400 is the right number. But anyway, the PFS, prime focus spectrographs, will be ready soon. And I think this attracts the scientists globally, all over the places, and enables the various international collaborations, including the ELOGITA with German, ELOGITA consortium, Euclid with the Euclid consortium, Roman with NASA, and Rubin with US NSF DOE. This is a sort of a visual introduction camera, and the fiber positioners looks something like this. And this is, so camera spectrograph is, I think you can, this reminds you some very good project, which is called SDSS. Right. So when you compare with, of course, the SDSS data, 8.2 meter super telescope can go deeper. And Princeton people actually led the SDSS program, and they noticed in the early phase that the Subaru is powerful. So they joined us. They joined the HSC project back in 2007, and we worked together since then on HSC and the PFS. And also we are working with Taiwan. They have a very good at engineering and doing science and their analysis. So they joined the HSC at the similar time, like back in 2006 or 2007, and then we were working together since then, HSC and PFS. So that's good. So Eurojita, we have this type of MOU and working together in the early phase, and we did, published papers on the initial commissioning field, 140 degrees EFETS field, and this is the list of the published papers based on the Eurojita and the HSC set. Those are all included in the A&A special issues on the Euclid initial data sets. No, Eurojita, sorry, not Euclid, sorry. As for the Euclid, we provided 5,000 square degrees imaging data in Z1 and obtained 25 PI data right in return. And the PI of the Euclid, the Yannick Merier, proposed this framework, and we agreed. And we got 40 Subaru nights, and that was secure, and through the usual proposal screening process, that is called the intensive program. So you submit the proposal to the Subaru normally and got the 40 nights and obtained the data sets. So this is how system works. Euclid covers this, infrared, but they don't have any filter on the optical data set. So they really need the color data from the ground. So we covered this area, Z-band, because Z-band is the hardest to get, because the sensitivity of the CCD become lower and lower as you approach to the 1 micron. But as I said, we have a very sensitive CCD in red, so we took this position. And all the bands are taken by some other partners, but G band is also taken by SprimeCam. We didn't use our time, but the Canadian people or University of Hawaii people use HyperSprimeCam to take the same words. So we contribute on both Z and G in a sense. But so this is how the Rubin collaboration works. So US Rubin requires us to contribute in kind. They don't accept the cash anymore. So we have to contribute in kind, and we accumulate some sort of contribution package in order to get 40 to 50 PI rights. And I think those still being negotiated, but yeah, we will give them the 50 Subaru nights over the 13 years. So 6 nights per year or something. And we would contribute manpower for the commissioning. And actually, this will be done by one of my former students. So he will go to the Chile with camera very soon. And also we would set up the regional data access center with a help desk and that type of things. So anyway, so because they are interested in the Subaru and all other items, they will be accepted and they will give us 40 or 50 API rights and so on. Oh, this is Roman, but it's okay. Time is running up, so I will just skip. So this is a summary slide. Subaru HSE is unique and powerful, at least for now, until the LSSD comes. But PFS is going to be unique, hopefully. And other instruments, including SKEXL, powerful, GLL, which will be covered by Koyama-san soon, will come. And as I said, some other works like CMOS camera or more to come. And so, introducing a new instrument timely is key for the to support the community in Japan and also the globally. And so that's our sort of strategy. And so this is the main reason why I'm here. Sorry, this is at the very end. But Subaru is looking for the international partners for the operations in order to be ready for the TMT construction phase and operation phase, because we clearly expect that I don't really expect, but it's fairly unlikely that the government cuts the Subaru operation budget once the TMT is construction become back online. And so we need, we are looking for the international partner and talk to various countries like India and Taiwan and so forth. But the framework of the international collaboration is being still discussed. We have some basic design, but because we didn't start it, it's not clearly officially. So there should be a lot of space of negotiations. But I hope that through this international partnerships, we hope we can provide you the partners observing opportunities and also the new instrumentation opportunities too. And that is both are, I think, very important to make the communities grow in the future. Okay, thank you very much.
We have some time for questions, comments, or even discussions. 임명심 의원님.
Okay, so I have two questions. One is about the international collaboration. So could you give us a little bit more in detail about maybe example, collaboration framework that could work in future? And another question is actually about your CMOS camera. So I was curious how good it is in the longer wavelengths, like at the red part of the.
Okay, let me answer to the easier part, my hobby. Your point is very important because the thickness is limited. It's not 200 micron. For now, it's very hard to get that point. So our thickness is sometimes like 12 to 13 micron. So that limits our QE in the red. So let me show you. Let's see. Where's Okay, hold on. The navigator, and where is it? Oh, I skipped my QE curve, sorry. Okay, should be here. Sorry, but I will send you the latest note, but at 900, no, at 800 micron, at 800 nanometer, the QE is something like 50% or so. So it's not so bad, but not extremely good. Okay. And also, the partners, as for the partnership, what we have in our mind is two types of it. One is a bigger one through partner, and the other is the associates. And through partnerships, if you have a full partnership, you would have a much more privilege to join the sort of operation, and associate is slightly limited. But and also, you know, the time on the obtained observing time is also, you know, scaled down. And so as for the junior associate, Juby, do you remember? It's going to be 10 nights.
It was 400K for 5 nights, 4.5 nights.
400K, but it's a freer scale. And I think, but it's still being discussed. And we might have to tune a little bit about the money, because the exchange rate is so different now. And our plan was laid out maybe 3 or 4 years ago, which is totally different. So I can't speak clearly about money at this moment, but something like that scale. And I have a lot of time to talk with you right here, or if I'm invited, I can about talk more. And but our strategy is that starting from the minimum, I mean, not from the big one. And if number of people increase who are interested in this type of collaboration inside this country increase, then it will naturally grow, and hopefully to the limit to that bigger collaboration. So I don't really want to work as a, you know, politically, but I really want to take some natural approach. So someone like him is interested in the program and try to get a small amount of money to realize this type of collaboration, and then hopefully, you know, it grows until some sort of a goal. Okay,
thank you.
Any other questions or comments? 지명국 회원님.
As a frequent user of HSC, I cannot thank you enough for creating, inventing nice instrument. So whenever we use HSC, there are always bad CCDs, several defective CCDs, and we have to plan around it. Do you have any plan to surgically remove those defective CCDs and replace them with a new one? If you cannot, what is the technical kind of obstacle?
Well, we definitely have a plan, and we have a backup CCD to be replaced in hand, maybe 5 of them. However, the question is when, because the HSC is super busy until today. But we hope that we have some time after PFS, operation starts. So hopefully, sometime 2026 or so, we will bring the camera back to the original place of Mitaka and do some walks. But I can't say when, because it depends on, many factors. But clearly, we have a plan. But our ultimate plan is that introducing the CMOS HSC by realizing the 200 micron thickness, which requires another, achievement and advance, and that is my also the interest too.
I have 2 questions here.
Yeah.
So about what is the data publication plan for the PFS survey? That's my first question. And the second question I have is the global collaboration you introduced us today are based on some unique data set that the other partners already have. For the future collaborations, do you require the kind of unique data set before you start the collaboration, or is it just okay to join there?
Sorry, I don't think I understand the second question, but let me answer to the first question first. So as for the PFS data distribution, there should be several ways, as we did for the doing for the HSC. One is you can fetch the raw data set and do by yourself everything. But we have a plan to do some preliminary or almost final, nearly final data analysis for the spectrograph, extraction and that type of things. So in addition to the raw data, you can fetch somehow reduced data sets. And if you are not the observer, like a theorist, you have another channel to access to the public or reduced data set, which is through the science platform. You know how it works. It's basically the Python interface, which gives you the access to the data and also the computing facility. And that type of, I think that 3 types of the access will be prepared. And so what is the second question? Sorry.
I'll ask you separately because time is up.
Oh, okay.
As Professor Miyazaki advertised, Dr. Yusei Koyama will give a talk about another instrument on Subaru in the second conference hall right after this session. So please check his talk. And Professor Miyazaki and Dr. Koyama will be here until tomorrow afternoon. So if you want to discuss the possible collaboration, please talk to him during this meeting. Let's thank our speaker again.
Thank you very much.